Absolutely.
All right. Good afternoon, everyone, and welcome to another Balerion Space Ventures podcast. Today we are speaking with Yanni Barghouty, founder and CEO of the Cosmic Shielding Corporation. Cosmic Shielding Corporation is addressing one of the fundamental problems of operating in space, which is radiation. As we push into longer duration missions that are deeper into the solar system, radiation exposure is a limiting factor for both equipment and humans. So, Yanni, we're really excited to have you here today and hear about your work.
Yeah, happy to be here. And again, everybody, nice to discuss the topic. I've been known to ramble on quite a bit on some of the nuances and the science. So feel free to jump in, Doug, if I start going a little too deep into the weeds, unless that's what we'd like to do here. So,
Well, we love to hear it. Love it if you go in the weeds, and you may get interrupted by the chat with questions too, which you already have even before we get started. So
sure.
I think it'll work. Before we talk about your company, what you're working on, could you give us your background and what led you into looking at radiation and cosmic shielding?
Absolutely. So, background is an interesting one. I've worked in quite a few startups in the past during my time at Georgia Tech. I actually worked with a few social networks that did pretty well back in the day. One was briefly with Yik Yak and their co-founder, Tyler Droll. Didn't end up working out. Then I was working with my own home sharing app that we kind of addressed we put together to try and address some of the issues that led to the kind of crash of those other platforms. After a while, though, I've always wanted to get back into hardware space. My background in the technical sense is biomedical engineering. My family, though, just as a further background, is multiple generations of nuclear physicists. So my grandfather, great grandfather, my parents are both
Hmm.
astrophysicists. Much more on the theoretical side. But from that network, Dr. Lumbit Seaver, our co-founder, he's been a family friend for some time. And after the last startup I was working with, I left just because we ended up working with one of our investors, Jim Clifton at Gallup, just doing some light consulting back and forth. And Lumbit was visiting, and we were just talking about the industry. This was back in late 2020, talking about how there's been essentially no major developments in the material infrastructure of space. Of course, there's always new, I'd say niche applications of new materials for sensors, thermals, et cetera. But some of the fundamental problems like radiation haven't really had a change. Then we started joking about the SpaceX Starship, the steel. We were saying that good luck sending astronauts to Mars with a thick steel layer surrounding their living quarters, wherever it might be, because steel, just because of the high Z of the material, it produces a lot of secondaries. And you can kind of, this is very reductionist here, but the amount of secondaries produced by material are somewhat proportional to the atomic mass of the target, right? So the higher, heavier it is, the worse it is for particle sources, whether it's heavy ions, protons, etc. So we were talking about, like what was really interesting at the time, and it's changed now. Space is a hot topic, but at the time, we were still getting a lot of investment, lots of new space was really coming into, I'd say, coming into its stride. And it's something that for the average person, you just would have passed right under their nose. And we were talking about how great of an opportunity there is to actually start to, get in early and make a significant change potentially on the trajectory of the development of space. That was something that's very exciting, have that impact on a almost planetary level, right? It's a
Hmm.
rare opportunity that you don't get in other verticals, other markets, etc. And of course, I've always wanted to get back into the hard science, hard tech space. He had his network across most of the major accelerator facilities, HIMAX, CERN, Triumph, Loma Linda, NSRL, so we could get really easy access to testing. And then, of course, we had the relationship with the MIT Institute for Social Nanotechnologies. And I was like, you know what? I think we can do this. So let's do it. And the idea wasn't anything magic. It's essentially we had a nanocomposite polymer, a proprietary polymer that had a higher hydrogen concentration than you'd get with something like polyethylene or any of the traditional thermoplastics, which was a lot of work in and of itself. And then it's very conducive to the addition of nanoparticles. So we were able to get a very uniform mix of a variety of nanoparticles. And after processing, you maintain that distribution, which again, that was to say the least, quite a pain to do. That took the majority of our time, to be honest, in development. Started working at it, and before you know it, there was quite a bit of interest, quite a bit of inbound. We got lucky with the early funding. Like, we got after we got serious here, let's say 2021. Oh, look, Michael Mealing says hi. Michael, we need to catch up. How's it going?
Yeah, you were early. I mean, 2021 really you were ahead of the wave of
Yeah,
when space really got recognized. And yeah, when you got your seed, that was good. Could you give us like so all of us kind of with investor background, a lot of space founders, but can you give us the high level view of the problem? What's the radiation problem? What
absolutely.
is it, that we're dealing with? And
For sure. So, as you mentioned in the beginning of this, it's one of the fundamental barriers to human space flight, human space operation. And by human, I don't just mean crewed missions. I just mean human operation in orbit, so satellites, whatever. Um, I like to say, aside from Delta V or getting up to space, it's one of the number one, it's the number one barrier. So traditionally, you're looking at particle sources, so heavy ions and protons. Those are the number one concerns, right? It's interesting because a lot of people like to characterize radiation tolerance using electromagnetic sources, so cobalt 60, but again, like it doesn't really have, uh, I'll save that for next up in the conversation because there's some significant issues with using that as a metric to gauge reliability in space. But
because right
regardless,
now you're talking about radiation from natural radiation from space, not
natural radiation
from our
space.
stuff, right?
Exactly. So the issue with these particles is, as you know, they can cause destructive events or soft events on targets, electronics, transistors. They can cause charge buildup, bit flips, et cetera, et cetera. Anything, all these events that can lead to either one, a crash of a system, total failure of a system, or an accumulation of errors that over time will lead to a catastrophic crash, wrong time, and so forth. And the traditional mitigation strategies, aside from the shielding, I'll get into that in a second, are on the electronic design front and software design front are pretty much all based on redundancies. And of course, there's some cases where they use alternative actual materials for the process. The feature sizes are larger, using different materials, spaced further apart. These things that can reduce the probability of an event occurring on the target. I'll get into the physics of why the larger feature size is important in a bit
Is
because
that what people mean when they talk about hardening
yeah.
electronics? Okay.
Yes, and sometimes they actually build the transistors out of different materials. That's like an extreme case, like for the very high-end red hard parts, purpose-built, require their own dedicated fabs and so forth. But a lot of the times, people use error correction codes, and again, those I like to. I mean, it really does boil down to redundancy. They do the same calculation 3 times, do a memory sweep, make sure that everything is uh, operating as expected. They send the same signal 3 times, and three is just an arbitrary figure. You can optimize this. But overall, as it sounds, that is the opposite of what you'd expect with something like Moore's Law, right? Like you get a significantly higher compute capability for the same power overhead, or there's a thermal and power overhead window, let's say, while simultaneously getting that improvement in performance. But in space, we didn't see that, right? So with the transition to both the whole new space boom, as well as the transition in capabilities to wanting that desire for real-time image processing, in situ uh, docking, maneuvering, all these applications that require, edge processing, right? There's been quite of an uptick in demand for high performance compute in space. That helped us quite a bit because that's where we got access to a lot of our initial demo capabilities just because there was such high demand. The rad hard alternatives, right, are one, they don't perform where you'd want them to perform for those kinds of operations. But more importantly, I think it's the cost and the supply chain is just not there to sustain these mega constellations that, especially in the past year, the amount of filings have gone off the charts, right? And there's just the volume's just not there. When you split it between the defense space and the commercial space, it's the main crux of the issue, I would say. So COTS, you have a massive supply chain that is very proven, right? You're competing, it's a terrestrial supply chain. You have AMD, the giants, right? AMD, Intel, NVIDIA, very robust. And of course, by nature, that has the volume necessary to drive this next wave of space, both exploration and commercialization from the data center standpoint, on orbit servicing, robotics, and so forth. So that's the issue we wanted to solve. We wanted to give manufacturers, operators, basically as much payload flexibility as possible, right? So you don't have to
Okay. So,
when
so you've got a natural threat, you've got a hostile environment that you've got to deal with.
yes,
We've got an interest in more compute, not less. You know, that's the data centers in space, all these things. And then the hardened electronics is just not going to be able to scale and meet that need. You're just not going to be able to do it. So you're gonna allow people to use a wider range of hardware up there.
exactly, exactly.
Okay.
And over time, it's funny because at the beginning, like back then, those early days you mentioned 2021, 2022, I'd say most people would consider shielding to be like insurance, I like to say, in the sense that they'll do it if they have to, but no one really sees it as anything exciting. It's very just a checkbox you have to get done.
Yeah. Right.
In the past 2 years, year in particular, there's been a huge transition in the idea of shielding as an enabling technology, right? Rather than
What did you just say? As what?
the idea of shielding as an enabling
Oh,
technology,
idea of
rather
shielding.
than,
Okay.
yeah,
Yep.
rather than just a checkbox that you have to make sure is, you're hitting
Yep.
the marks on so your system will survive, right? And that is really driven, I think, a lot by the data center side of things. But of course, we're seeing, bleed in from other applications where certain defense applications, you have a need for hardened components. And there's been some shortages lately that have led to, significant attention in investigating rapid deployment of, let's say, COTS for defense applications, as stand-ins for the mil spec and rad hard, rad tolerant chips. That's actually an area where we're getting a lot of our traction in addition to the commercial space. So yeah,
Because
yeah,
you want to use a certain compute in space, and right now you can't do it, and your technology can enable that. You can allow this to happen now.
absolutely. And we've done it, actually. We've been
Right.
flying. We were the first ones to fly, I think, at the time, the fastest device in space, which was a Jetson-based flight computer
Mm-hmm.
in 2024. And that's been operating since. One cool snippet I'll give everybody is that it's been 2 years and there were 42 total functional interrupts on the device.
Okay.
And based on the expectation with alternative shields and like everything we've seen on the ground and other systems on orbit, you would have expected an order of magnitude higher if it wasn't shielded, right? So this is a really interesting thing, and we'll be publishing some data on this in the next coming weeks, hopefully.
Okay.
So the idea is that yes, we enable you to use the flashy AI-capable devices in orbit, but also even if you're happy with the existing performance of your electronics, we can also give a significant mass reduction without sacrificing any volume. That's a key point as well, right? So you can essentially have just more efficient subsystems. And that's where we do a lot of our work. We work with subsystem developers, manufacturers, to
Okay.
optimize their design or to enable, again, flexibility in payloads.
Okay. Yeah, so I kind of wanted to hear about what your solution is. Before we get there, is there anything else we need to understand big picture on radiation? Like, is there certain types that's coming from the sun, is coming from deeper outside the solar system, and then you'd mentioned this, I guess, what's secondary radiation, where the material of your craft gets hit and then creates other stuff. Is that
Absolutely.
basically what we're dealing with?
Yes, yes. And this secondary radiation is a very, very important area of focus for us right now. And we're trying to improve the characterization of basically so there's old tools. I'll just take a step back, right? Sometimes people would use this tool called Cream 96 to estimate the expected error rates for a device. Now, Cream 96, and they even say it in the README, but I guess people like to ignore that, which is I ignore READMEs all the time, so I don't blame them. But it does not give you an accurate reading under 90 nanometers, right? Essentially, it has some issues with the way it calculates the reaction cross section, which can give you essentially, to be honest, borderline useless results, right? You're going to get a very
Because that's an issue when you're dealing with more modern types of compute.
exactly,
It's just not fine enough resolution.
exactly.
Okay.
And we did a very, very long-term study on trying to kind of patch in some of these issues in the diagnostic side of things, because that's one thing too. When you're talking about solving such a fundamental issue, right? You're going to be rightfully so met with a lot of skepticism because you're claiming to solve something that, people thought there was, there's some physics barriers to providing a better solution than what we're currently using. And it's actually not necessarily that there were physics barriers. There was basically a disconnect on the applied physics that the engineers were using in space, essentially, like I'll get into that in a second, and some of the more modern understanding of, target fragmentation, spallation, etc., the nanodosimetric effects of radiation that were being overlooked by both the modeling tools and the industry by association, right? And our CTO, Dr. Limbit Seaver, he's actually his claim to fame in the physics world was basically improved characterization of so heavy massive particle transport through materials and
Yeah.
the creation of these secondaries and so forth. So a lot of his fundamental physics work is applied in many of the models companies use today. So whether it's HZTran, AP9, even AE9, lots of these codes, right? So to the point, it wasn't just like, there was, of course, the material side of the development, but it was also that there were traditions, to put it simply, that the industry followed that were outdated. And because, they got the job done for some of those larger feature size devices, the older devices, there wasn't really an incentive well, there was an incentive, but there wasn't a very strong need to kind of rethink the way we shield devices. So we started this long evaluation over the course of honestly, since I'd say 2022, since the early days when we actually got material out of the lab at HIMAC, Triumph, CERN, Loma Linda, Oak Ridge National Labs, on
Hmm.
orbit on the ISS with that mission, where in 2024, even where we had the NVIDIA, that was, I think, the kind of like nail in the coffin for the solution, I would say, like where we really got the understanding on how we can predict performance based on shielding depth. We also had this 8-month mission on board the ISS in 2023, where we were using that as kind of again, like something to help us build up this semi-empirical model that we use to assess radiation risk, but
So
also
you're putting your composite material up in space, and then you're just characterizing it. You're seeing how it works up there, and
absolutely. And we did
yeah,
that. Yeah, those were what I
yeah.
call the scientific demos, right?
When was your first mission? The first
20,
the first flight?
20, it was AX2 with Axiom
Okay.
Space.
Oh,
So
cool.
that was returned, and we actually have the payload. We just had a bunch of active and passive detectors
Hmm.
inside a shielded CubeSat. It was a box,
Yep.
and it was on board. It was with that resupply mission, and it was inside the ISS. But you can model and account for the attenuation of the actual structure, and then he tried to use that to kind of create a little bit of like I said, a semi-empirical model based on what we saw in space and on the ground. And as we developed, that just got more precise, so to speak, right? We initially were working off of like a phase two, for example, during those times where FRL, basically the idea of proving COTS in space, right? Like how can you make that happen with reliable operation. Then we actually expanded that to attack PHI because of the need to rapidly diagnose and do
Nice.
quick swap. And then
Yep.
actually now we have a sole source and a kind of program with the DoD that we managed to get through the Senate appropriations process that's rapidly expanding and ties in more to the defense side. But these things, once you can showcase that the science is real, right, then you start to see that cascading adoption. But I can talk about I'll talk about the science at a later point, but let you jump in with questions first because there's
Well,
some
it's it's not just the science. It's the science of. It sounds like you're validating your product is what you're doing. What I'm
absolutely,
hearing you doing. Okay.
absolutely,
Yeah.
absolutely.
And
And
what was the insight that you guys had? I mean, it sounds like you figured out. You said you had a composite that has a high hydrogen density, which I assume that's the weight that you want for to have effective shielding. You've kind of because I guess you want it to be not too heavy.
mhm, mhm.
Um, and so you guys have managed to produce a type of material that does this better than whatever we've done in the past.
Yes, yes, and it's also very conducive to the ad- addition of a high concentration of nanoparticles, various NICs, which is in the past. I'll give an example. There's been Mitsubishi's Boratron, which is a polyethylene and boron composite, right? The problem with a lot of polyethylene and a lot of thermoplastics is when you add in a lot of nanoparticles, especially at higher concentrations, they tend to get brittle, right? And we've had customers where this has been a serious issue. And they're like, we wanted to use this, but it was hard to integrate, right? That was a very recurring issue, especially with the larger customers, like in terms of more established ones that have, investigated this for some time. Then, of course, there's just the performance benefit. Like, yes, it does out. Currently, it is the highest performance material that has been tested for radiation shielding from a variety of sources. Of course, we can optimize it to specific sources. So we can actually adjust concentrations if you're more focused on, like, thermal neutrons, as an example. And, if you're worried about RF, EMI, then yes, we can adjust some concentrations for those applications. But the key was that we didn't want to just have an effective shield. We wanted one that was easy to integrate because you could have the best shield in the world. If it's hard to integrate, the engineers are not going to use it, right? So you can't have something with a low melting temperature. You have to have very good machinability properties, which we
Hmm.
do. So you can actually just CNC this thing in place of the aluminum structures you would be using. The ability to modify it to actually act as a structural material or a thermal interface. This is something we have done. So like you can have this, just anticipating the rising adoption of NVIDIA parts like GPUs with very high thermal outputs. We wanted to have a dual shield slash thermal interface. Right? So again, like it's the whole picture here, not just the radiation performance, but also the realism of integration. Like, how easy is this going to be for engineers to adopt? How quickly can they adopt it, right? And how flexible is it to various mission parameters, geometries, et cetera, et cetera.
Okay, and I think you answered my next question. Just want to make sure I understand it correctly. But when you're shielding something, it sounds like the answer to this question is everything. But is it like you can say, I'm just going to make a box for this processor, I'm going to make something for this cockpit, I'm going to make the entire ship protected this way. How's the shielding used, or where is it used?
Absolutely. So for the most part, it is basically enclosure swaps or spot shielding, as you described here. Like, so basically a customer will come in, say they have a flight computer and they're like, hey, here's our existing step file of the enclosure. Can you design something that's either more effective, lighter, etc.? Sometimes they have very detailed targets on the fluence of various particle species and energies, right? That they want us to focus on, and we optimize the depth based on that. Various, degree of detail is provided, like because that's the thing. As I mentioned earlier, there's quite no set standards in terms of radiation protection yet. I would say in terms of how
Hmm.
thoroughly is qualify their systems. It's all over the place. But then we design some custom integrations, whether it's a full enclosure swap, right? Like they're just replacing this entire thing with a
Okay.
alternative, or it's just inserts and so forth. We are actually moving towards doing end-to-end integration. So this is like this year what we've been focusing on. So
Hmm.
for example, oh, you want a VPX3 slot enclosure for X, Y, and Z devices that you use, right? We handle it end to end, looking at the machining of the aluminum structure, just if that's something you want, right? With the shielding taken into account, we do a very complex model of the radiation field inside the target or at where the target would be. And then the basically all under one roof, right? So you don't have to have several different vendors for your aluminum parts, your, plasteel parts, and whatever else you might need in this enclosure.
Okay. So
Basically
there's
looking
two
to see.
problems. It's the type of radiation that you're trying to shield, and it's also the thing you're trying to shield needs maybe different types of protection from different radiations. So you have to
Yeah,
optimize for those two things.
exactly, exactly.
Okay.
And to simplify the integration process, that's this what I just described as the next step. So just like basically taking around removing it's all custom, right? And space is moving towards, I think, standardization slowly, but for the most
Mhm.
part, every manufacturer, every operator, every satellite bus manufacturer, subsystem, OEM, etc., they all have their own small nuances and variations in design that you have to accommodate. So we're just basically trying to simplify the end-to-end process so they can have a single vendor for all their structural needs, including the capability of enabling COTS for their structures, right? But at the
Okay.
same time, we're also looking at terrestrial applications where we're getting, I was surprised initially by the amount of traction on that front, where we're looking at chip level integrations. So actually replacing some of the ceramic gold packages on some actual, at the chip level, being with plasteel. Just so happens that the thermal characteristics make it feasible.
Okay. And is any relation to there's this nuclear renaissance going on? We're going to start mass producing small modular reactors, things like that. Is there any relevance to that?
Yes, yes.
Okay.
That's one area of focus. RTGs,
Okay.
isotope is
Yep.
basically an area of focus there. There have been some surprising ones. Like I'll give you an example in commercial aviation, right?
Okay.
Or we had someone come in, a major manufacturer here of of devices for in-flight entertainment. And they were saying like, hey, yeah, we've had too many complaints from airlines about having to issue vouchers, credits to customers complaining about the entertainment going offline uh, flights, right? And I was saying I would love for that to be the issue, for it to be radiation, and we can just solve it with the plastic. I don't think that's the case.
Yeah.
But
Right.
lo and behold, these modern flash storage devices, these NVMe's, and we've tested a lot of VNAND flash devices, some other flash devices, not from Samsung, as an example, and they're extremely vulnerable to secondary neutrons, right?
Hmm.
So
Okay.
the thing about secondary neutrons is people tend to overlook. It's not just displacement damage. There are actual physics mechanisms by which they can cause ionization of a target by the creation of secondary electrons. So these delta electrons, right? And that is what we think is causing a little bit of a underestimation of, why didn't we see this coming in terms of,
Interesting.
yeah, yeah,
Interesting.
yeah.
And that's that's a good example of I guess the location you're dealing with is important. I mean, their aviation's higher up. It's obviously have more radiation than on the ground, but it's not quite in space. And
Exactly.
then is it different depending on where you are? Is there an issue if you're in LEO versus GEO versus going to the moon versus going to Mars versus going to deeper space?
Absolutely. So, like again, an example on the moon, something that again is often overlooked is that a lot of your effective dose is from secondary neutrons, right? Just because there are a lot of high Z elements in the lunar regolith that cause the emission of these secondary neutrons.
So
Now, in
secondary, not from your equipment, but from the moon itself.
on the moon itself,
Okay.
and in on a terrestrial setting, when you have an atmosphere, right, the distance they would travel wouldn't be significant, but they can be significant enough in some lunar applications, right? But then, of course, you do have the heavy ion exposure, and if there's a solar particle event, then could be an issue, especially if you're not in the period where there's a little bit of protection from the magnetic field. Um, I would say though, when it comes to, it's interesting because we have some geo missions coming up, and one interesting one where there's going to be a very long transit in mid-Earth orbit. And there is a very harsh radiation environment in MEO with the Van Allen belt, but the thing about electrons, like that's what's really dominating that space. Of course, you have a lot of trapped protons still, even though there are some at little higher energies that are very relevant to
Hmm.
operations. But the electrons, it really exponentially drops off this actual effective dose with very minimal amount of material, right? So we tend to optimize for the heavy ions and the protons, because if you get the fluence, so basically we look at the differential flux versus LIT curves from proton trap proton, like solar particle event trap proton and heavy GCR sources, and we make sure that we have a conservative shielding depth to hit the mark for whatever device we're looking at. Again, there's lots of moving parts here, so just to summarize it that simply, rather than looking at, say, the electrons. Just because for the most part, 5, 6, 7 millimeters of anything, and if you're looking at geomission, you tend to have that kind of depth when you factor in the entire bus. Yeah, you've knocked out 99.9% of the effective dose from electrons, right? So they don't really have a lot of
Interesting.
stopping power or penetration depth, sorry. Um, so yes,
And just so everyone knows, GCR, that's galactic cosmic rays.
yeah,
And then you have this additional factors depending on what orbit you're in, where you're at. So,
exactly, exactly.
okay. Um, in addition to, it sounds like your customer base is actually kind of runs the entire spectrum. I mean, it sounds to me like you already described one I wasn't expecting to hear, which was aviation on Earth. Already some potential civilian nuclear power, which is also not one that was on the radar. And then the obvious ones, I think for us would be NASA, any new commercial space applications, and then DoD / Space Force, I guess.
Exactly. So there is also a growing inbound we've been seeing from drones, for example, like high altitude drones. Drone swarms is an interesting thing coming up
Okay.
where you have,
Like aviation, where they're on Earth, but getting to elevations to which it becomes significant.
Not just that, but also military applications too, where
Oh,
you
okay.
have a
Yep.
very low tolerance for upsets, even though the probability is low,
Got
right?
it.
So because you're at a lower, I mean, you have a lot of atmosphere protecting you.
Okay.
But one of the things that is really driving that adoption change is basically the idea of rapid swap capabilities for COTS in place of mil-spec and rad-hard components, right? That is something that we have been making quite a bit of headway in, and I'd say is really driving a lot of adoption on the terrestrial side, meaning not in, well, under LEO, right? VLEO, we're also getting some interesting cases where, for example, even though you do have increased attenuation from, being from the atmosphere, right? And also you just significantly lower orbit. The if an event occurs that does cause a reset or a system, like a momentary failure of the system that you can recoup from, while you have that much atmospheric drag, you can't afford to essentially go offline for 30 seconds, a minute, right? Your
Okay.
system might fall, you might actually crash the actual satellite, right? Whereas
Okay.
if something goes off, you need a reset over the course of however long, there's a lot of time uh, to account for that error, right? To actually get everything back
Right.
on and so forth. So that's an interesting one that I didn't expect as much interest in, but VLEO has been a good driver as well. But
Okay.
yes, to your point, it's across all verticals. And now we have 8 systems, commercial systems currently in orbit. They cover cameras, flight computers, and some power control systems as well.
So this is this is already existing customers with your product using your product.
In space, yeah.
You said 8 in space?
Yes, yes.
Wow.
And we
Okay.
have another 8 going up over the next year. Again,
Okay.
more. So
Okay.
I'm surprised by the amount of cameras. It kind of makes sense. It's the same mechanism for like when you get those stuck pixels, dead pixels, accumulation of them on
Uh-huh.
CCD. It's the exact same mechanism as you get any single event effect on.
So you're finding that you have protecting the cameras is a big interest?
Exactly. So we do a
Okay.
lot of backplane overwrap designs for
Uh-huh.
covering the CCDs. We work around thermal interfaces for some of the more sensitive devices, but yeah,
Yeah.
that's essentially.
Okay. I was going to ask you about your business model, and I think you've almost gone through it. And if I have it correctly, but it sounds like there's an analysis component of the environment. There's an analysis of the target you're trying to protect. There's the material you're going to provide for the shielding, and then it sounds like there's also kind of I don't know what you'd call it, a fabrication or customization for for the application or something. Is that it's kind of end to end is what I'm hearing.
That's correct. That's correct. And the the analysis and design part. So one thing we're working on now is as I mentioned, that semi-empirical model I kept, dropping hints about is basically a tool for modern devices. So nanometer scale feature sizes, single digit nanometer scale feature size,
Uh-huh.
a way to get a very precise and quick estimation of your projected error rates based on certain shielding depths, not just with our material, right? We're going to release this as a tool just for anybody to use because that's something I don't want to keep doing. I don't want to keep doing the analysis under our visibility.
Okay.
It's
Got
a
it.
lot of because
Yep.
so there's a few approaches you can do. You can use tools like Omer, FastRad, TRAD, SpenVis, Alteris. We like to use some of the more sophisticated models that are a little more
Hmm.
precise and quite a bit more precise. I'll say not a little, like the particle heavy ion transport code system fits. Geant 4 is also a lot better. It's these 3D Monte Carlo tools. And that takes a lot of compute power, right? So we use a lot of HPC
Okay.
to do these
Okay.
models to get a very precise or very accurate representation of the radiation field in the target area. So we're moving away from just doing the simulations, and we have done so many at this point that we have quite a bit of, like, for example, for most LEO orbits that realistically a company would use, we have basically pre-calcs done, pre-calculated environments.
You know, it sounds like you know what to expect within most of the environments that you're going to be
Exactly.
dealing with. Yeah.
Exactly. And of course, there are always exceptions. Like sometimes
Yeah.
there's an extremely high value mission where you want to shield, and the customer is just like, yeah, we need a full analysis done. That's
Yeah.
fine, right?
Okay.
But moving towards standardizing the integration process is the next step. So again, doing these enclosures, these all-in-ones, right? So you don't have to
Yep.
think all these other vendors just built. Here's the built component or built structures for your device. You don't have to
Yep.
worry about the shielding aspect. Just tell us what component you want to use. This thing will do, right? Uh,
Right.
So that's the transition. And then, of course, the chip level integrations that we're moving towards are going to have a little bit more of terrestrial overlap.
Okay, good. And and then what's your company like right now? How many employees do you have, and what location are you at?
So we have had a compact team. We have about 11 mix of part-time, full-time, right? There's a
Hmm.
core full-time team that's been pretty much the same until the past 6 months. We've been, increasing the team size. We're going to be hiring another probably 10 in the next year.
Okay.
So we have rapid expansion plans. Everything is now centered around Huntsville. We have a new HQ slash prototyping engineering facility that has, the basically, fully certified clean room, et cetera, et cetera. That's
Okay.
coming online in May 1st, actually.
Great.
Um, so basically, we do work with a lot of already, high volume machine shops and some of the more kind of I don't want to say this to offend anyone. Some of the more basic applications, like where we don't necessarily need to buy 20, 30, 40 CNC machines and get an AS9100D certified in-house production line. We do all the
Sure.
prototyping and design. You think about it like a kind of like Qualcomm, right? Like a fabless uh, designer, right?
Okay.
Of course, now we are moving a little bit to more closer integrations with our scale manufacturing partners in order to do those all-in-ones. But essentially, that's been the approach here because I took an approach where I wanted to minimize the amount of funding we took in just for dilution's sake because of the sheer amount of technical humps that you have to overcome to be taken seriously in this field.
Hmm.
So, for example, like, we wanted, if it wasn't for like our co-founder's history, for example, I think it would have been a lot more difficult to do this as cost effectively as we did. But just because of his time, with these facilities over the past 40 years, where certain companies had to request, a year, 2 years in advance, even the big guys, for some NSRL beam time or heavy ion time at X, Y, or
Hmm.
facility, we were able to sneak in on weekends, basically, get the excess hours and run hundreds of hours of tests over the
Oh,
past
cool.
several hundred of hours. We're
Hmm.
still doing that. We're still running a lot of tests just because there's
Yeah.
always systems you characterize. But what we want to do is make sure we figured out the science first. We had bulletproof characterization because again, like you'd have customers like this is actually a good example, right? Like imagine if you're looking at the equivalent of a car crash test, right?
Yeah.
The thing with how radiation like because it's again seen as a black box almost radiation physics for a lot of these integrators, there's a lot of questions that are kind of redundant that pop up. Like for example, customers will say, okay, have you tested to an LET of X, like a high LET target, what they think is a high LET target? Because if you've tested X, Y, and Z below it, but you haven't tested that threshold, it's not going to work. The thing is, it's not a deterministic increase in probability of an event occurring with a higher LET, right? It's stochastic, which means that you can have an LET of 10, and I'm just shorthanding not putting the units here just because sake of time,
Yeah.
that has a higher probability of causing an event on most targets than an LET, a particle with an LET closer to like 50, 60, right? And this is something we wanted to showcase at CERN, and we had this really complex test with a very high sample size of devices to say, like, you have to look at the bigger picture here. So, for example, like, there'd be cases where imagine if you're doing a car crash test and you're testing your airbag, and we're like, okay,
Yeah.
airbag worked at 83 miles an hour, just a, full stop collision, but will it work at 82 miles? And it's just like, in
Gotcha.
physical sense,
Yeah.
it's like, why? Yeah, of course, right? But,
Yeah.
because it's seen as like so, I guess in some ways fluffy, like the
Yeah.
application
Yep.
of science, you sometimes have to do a lot of these redundant tests and simulations for customers for them to take it seriously. It's
Got
fine.
it.
Like I'm happy to do that. But that's why we spent so much time at accelerators, making sure we
Yep.
hit some marks, right? And the next step was production. Because there were times when I thought we were ready for production, and absolutely we were not ready for production. Like
Okay.
stress testing.
Yeah.
So we were able to make sure that we knocked out the core science or the core scientific quote unquote unknowns, the engineering unknowns and the scalability unknowns before starting to actually, offer the product as a product. So I'd say that's an approach that we took. We didn't want to rush into it because again, like with something like this, we could have raised like, hold on, if we raised our seed round a year earlier, right, and decided to just go straight to the customer side and the biz dev first before tackling the science,
Yes.
what you would do is just ruin your reputation, right? Like it's a little
Okay.
different from doing like, soft circling a larger product. There's a low level integration, so you have to deal with low level challenges, right? The very
Right.
engineering and science questions.
Right. So you're going to be approaching, when you do look for capital, you're at a point where you've done a lot of de-risking. I've heard kind of two parallel paths. You've done a
Yeah,
lot of the science and validation that's still going on, both on Earth and in space. And at the same time, you have made products, you have paying customers using your product now in space. And
yeah,
this has kind of happened through a combination of non-dilutive funding. Sounds like kind of a lot of sweat equity slash creative ways of getting it done and non-dilutive funding. And then now you're getting ready for this next step in Huntsville to kind of take it up to
exactly.
the next level.
Exactly. And it's funny
Okay.
because I don't know, right? Like I think we're seeing a massive shift in the VC approach to space, where I think early on there was a little bit of a hyper focus on the large, flashy system level, like building, moon factories, building rocket ships, which I'm just an
Yeah.
made up example, but you go what I'm saying, right? Taking like the Silicon Valley approach and applying it to space. But I think it's a rare occurrence just in human history, but when totally new markets open up, right? Like space is a brand
Yep.
new frontier, right? There's no, it's like when transistors became a thing, right? There's an opportunity. It's in the actual fundamentals, the infrastructure that makes that possible. You can't just jump ahead towards like I want like Starship Enterprises right now, right? Like, there's a lot of
Yeah.
legwork you
Yeah.
have to do to get to that point, and a lot of it is on that's seen as not as flashy. The material infrastructure for that, the built infrastructure, standardizing the buses, right, which is very important. Standardizing X, Y, and Z subsystems.
Right.
Uh, and I do think we're seeing in the past year quite a bit more, I think, respect from the VC space for those applications, and they've been warming up to like the critical technologies to enable this long-term just operation in orbit for humanity. And that's one reason we've decided to start, opening up more, going just being a little more aggressive. Because with how basic of a demand, or like not basic is a good way, how fundamental the demand is for such an application, like
Yeah.
well,
It's such a fundamental issue. Yeah.
you do get a big pipe, right? But if you're not
Right.
careful, you can again sully your reputation very quickly. So
Yep.
luckily, we've been able to navigate, I think, effectively in the sense that we have essentially unlimited runway as a business now. Again, we're a very small team, but we're still able to we have profitable quarters and so forth. But with the sheer amount of filings you're now seeing, the plans for these mega constellations, we decided we're going to put the gas on a little bit, start ramping up more aggressively. Luckily, as you said, we have this nice positioning of the commercial and defense space where, we're getting direct support on the actual defense budgets now, going forward and for the foreseeable future to accelerate the kind of scaling infrastructure on the manufacturing side. And now it's just about productization and just streamlining that ease of integration to customer journey.
Right. Right. I mean, and one thing that's really interesting about what you're doing is there's a lot of really interesting things in space, and they have their application. Like I've got this product that's going to help us get from Leo to Geo, or this other thing. But when you're talking about what you're doing with radiation shielding, I mean, as you've described, it's in everything. It's on Earth. It's in Leo. It's in Leo. It's in Geo. It's every single thing that's going to operate is going to need this issue addressed. I
Exactly.
mean, your total addressable market is the entire aviation and space economy.
Exactly, exactly. And in order to make that real, right, like what we're doing is I want to make it so that the customer does not have to think beyond a certain point about radiation, right? They don't have to do the complex Monte Carlo simulations to model the radiation field and whatever
Mhm.
and component. If we're going to essentially get to a commoditized space industry, that
Yeah.
process has to move a lot faster. So that's why now we're moving into just saying like, here's a plug and play enclosure for X, Y, and Z. We can modify it to a certain degree to fit whatever bus you're using, whatever chassis you're trying to put
Yeah.
into. But don't worry about the field. This is rated for anything up to an NVIDIA Thor, blah, 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 right? Like just some example, like shorthand on the kind of specs, making it easy to understand for the engineers.
Yeah.
Like, Leo, NVIDIA, 10 years, right? Like,
Yeah. They're
simple,
going to be able to take you for granted in a good way. It just be like,
exactly.
whatever we're going to do. Yeah.
That's what I want. Exactly.
Okay. That's cool. So what is it? So then what is Cosmic Shielding Corporation 2035? What's the sequence that that you see going forward and where it ends up?
Yeah, so that's an interesting one. 2035, I'd say I'm hoping plasteel is just a boring standard in every single compute element in orbit.
Okay.
Uh, Kind of like Kevlar for bests, right? Like
Okay.
something people use, it's integrated everywhere. But more importantly, I also want cosmic shielding to become a structures provider because that's one of the things that makes that possible, right? Like for it to become such a common, like, household name, there's a lot of things that need to be simplified with the industry. We've had complaints from customers where, we have high machine tolerances or like, very a good fidelity on precision for our CNC process, but because they're using three, four other vendors for the actual aluminum structures, some copper interfaces, et cetera, um, it doesn't actually all fit together. And then they have to go back to drawing board, get like, it can cause complications. That's a very common problem we've seen. So having that under one roof, becoming the, let's say the kind of like the Amphenol of space. You ruggedize electronics for space. Customer
Yes.
doesn't have to do more thinking beyond that. Just ruggedize it for me, make it happen, right? And we provide those structures. So the
Okay.
built infrastructure. And I think that's, it's a symbiotic approach with like the bus standardization. It's just at the
Yeah.
level, right? But first the subsystems, then the buses, then who knows?
Okay.
The wild card is, of course, the chip integration aspect, because that can
Yeah.
probably, you're talking about volumes in the millions in that case, not just in the thousands, tens of thousands.
Okay.
Yeah,
I should have asked you this earlier, but how much will you protect humans with this? Is going to be a component of this?
for sure. So we actually have a upcoming Space Act agreement with Marshall Space Flight Center to basically do end-to-end de-risking for Artemis applications for human space flight.
Oh, cool.
So,
Okay.
we will be doing that.
Okay. And that goes back to, you're looking at your targets. This would be a different type of target you're protecting
Exactly.
with your material. Okay.
And honestly, I would say it's going to be the same material. It's more so like, of course, there's going to be some optimizations you do on like, making sure you do the blood forming organs of the body, like our number one for protection. But
Uh-huh.
it's also the degree of qualification is a little higher when you have the human space, right? So you're just going and just requalifying from the beginning. It's a good opportunity to do that. And it's something that, I want the Blue Origins of the world, the Intuitive Machines, or the companies who are working on Artemis adjacent activities. I don't want them to question whether or not this is qualified for that application. I want to, get that stamp of approval directly from the source and say,
Yeah.
it's human rated for Artemis.
Cool. I'm just reading through the questions here, see if we missed any. Yeah, I think you got them. Um, okay, very interesting. And then I guess the last part of this would be, we've heard about the product, we've heard about the science, the de-risking, making a product that actually manufacturing it, having customers use it initially, and then how do you scale? I mean, how much of that is a component of this, your endeavor?
Yeah, so the plans for scaling now, it's basically just there's like as I mentioned, streamlining that customer journey. So for the time being, there's a lot of custom integrations, right? Of course, there's certain
Yeah.
companies now working with who have significantly higher volumes than some of the new space startups. So that
Uh-huh.
these are always nice accounts, but it's still custom. So the next move right now is one just basically more engineering bandwidth, which we've been, hiring for these positions now. And then, of course, the actual business development side, streamlining the onboarding process for the customer, simplifying their understanding of how do we integrate this, right? Because that's a question that happens all the time. They're like, I like the performance, but what do I do with it, right? Like, how do I actually use it? So
Yeah.
on that front, like, this effort in Huntsville is basically to set up. Right now, we have, the base capability for base plasteel to integrate in the current format. But we're now standing up this end-to-end system. So basically, we'll be able to do, full structural integration and design and production, no matter what it is, even for the components not using plasteel that will have
Hmm.
be necessary for the device, right, or for the structure,
Yeah.
well as the qualification, shock vibe, TVAC, even some proton irradiation, and of course, cobalt 60, but cobalt 60 is a little, again, not that useful
Okay.
for certain applications. It has uses. I'm a little harsh on it, but
Okay.
Yeah, that's essentially where we're going. And of course, now we have opened up a new round. We're doing a Series A. It's
Okay.
pretty good deal.
Series A is open now.
Open now, yeah.
Okay.
And we are focused on the strategic side just because I think that makes a lot of sense with our business, with the dual use aspect in the defense space. But
What do you
yeah,
mean the strategic aspect?
so strategic being like companies who are technically familiar with the applications and the problems. So,
Okay.
it's like,
Got it.
yeah, exactly. Like Moog as an example. It does a lot of subsystems, lots of standardization to happen there. There's
Gotcha.
some chemical companies actually we're working with on this who are going to be participating. But
Okay.
that's the kind of cohort I'm putting together here, just because I want to make sure, as you said, there's so many different verticals you can hit. I want to make
Yeah.
sure you have a little bit of a leg up in each one, right?
Yeah. Okay. This is extremely interesting. I mean, it's like we've repeatedly said, it's just such a fundamental issue. You've come up with an effective solution for it, and are really growing and integrating into the economy in a meaningful way. Is there anything else, anything we missed or anything else you kind of wanted to get out to our audience before we finish up?
Let me think. So, a couple things on the science front, but those are like very nuanced that I'll say for later. But just
Yeah.
one summary that we're going to be publishing some of the data from CERN for everybody to see. It's going to be presented at IEEE or NSHREC conference
Okay.
coming up in the summer.
Yeah.
Then also at IAC, and essentially it's going to answer the questions of why didn't people look at shielding and alternative shielding? Why hasn't it become widely adopted in the past 10 years? There's some
Okay.
really interesting findings there that they're a lot simpler than you would expect, right?
Okay.
Basically, I'll just put a snippet. When engineers look at unrestricted LET, right, they're looking, it's in the physics world, it's not as widely used these days to characterize radiation effects on targets. It was maybe 20, 30 years ago, right? But it's a one-dimensional measurement. So it's coarse. It's a very coarse measurement. And we're
Okay.
finding that there is a very low correlation of unrestricted LET and fluence. I mean, fluence is different actually, but these unrestricted LET versus fluence on the expected error rates for modern devices. There's a threshold somewhere. Like maybe it's below 50 nanometers, maybe it's 60, but there's a very clear break where nanodosimetric properties take over. Some ionization density, delta electrons, right? These Nila effects.
So there's a band in which you can use LET, and then you're trying to establish what that is and what the
Yeah.
alternative would be. Okay.
And
Got it.
and back in the day, it would have had a strong correlation with event rates, but now it's starting to break down a little bit with these modern
Got it.
devices. And
Because of the smaller, like because of the new modern electronics? Okay.
yes, and this is something that will be relevant on quantum systems. It's very relevant on biological systems or for DNA strand rigs.
Hmm.
At CERN, we went and we demonstrated this in practice. We showed, hey, let's give you we'll come up with an estimate of the error rates based on this traditional way of doing it, and show you
Yeah.
what actually happens. And the disconnect is huge, right? So
Interesting.
really interesting stuff there. And we're doing it again at CERN, by the way, in October or November, I think,
Okay.
later this year. Um, just again, reiteration there. But yeah, so I think the science is there. It's nothing magic, right?
Yep.
The real answer here is how do you make it as easy and painless to solve such a annoying problem? Because it is an annoying problem for a lot of the industry, the ones who want to really make it splash in space.
Yep.
They don't want to have to be restricted to hardware from 10 years ago, right? They want to use the
Right.
cutting edge components, and that's what we make
Right.
possible. Just adapting costs for space, bringing Moore's law to orbit. That's how I like to say it.
Right. Yeah. Like we said earlier, it's not only are you addressing a fundamental problem, but you're enabling the use of more technology in space through this.
Exactly.
Yeah.
All right.
Great.
All
But
right.
Yanni, this has been very interesting. I think we've all learned a ton. It was really good talking to you, and thank you for joining us today.
No, it was a pleasure being here, and I love the questions. So again, if anyone has questions on radiation and just curiosities, feel free to reach out to us at any time. We'll be happy to answer.
Sounds great. What's the best way? Website, LinkedIn, that kind of stuff?
Website is great. LinkedIn, I check it all the time, but website's always the best way. Just going through the info request and so forth, or getting my direct email. Yeah, yeah.
Sounds good. Okay, Yanni, thank you so much.
All right, take it easy. Have a
Yep.
good
All
one.
right. Bye-bye.